this computer. Okay, so we talked about the simplest type of motion, which was rectilinear motion for particle. So particle moves on a straight line, as I explained, and you already knew possibly. You need only one single parameter to define the motion, which means the position, the displacement, the velocity, the acceleration. You need only one parameter. You take the derivative of position, you get velocity, the time derivative of velocity, you get acceleration, and you move forward. Then we talked about non-rectilinear motion, which is obviously curvilinear motion. You need more than one parameter. The path of motion is curve. And as I mentioned at the end of the lecture, there are different ways to analyze this. You can use Cartesian coordinate system. You can use normal tangential coordinate system, or you can use cylindrical, or in two-dimensional motion, polar coordinate system. I think you guys are familiar with Cartesian, obviously XYZ, and cylindrical from your math courses, right? Normal tangential is not something we use in the math because it's more meaningful for dynamics. And as we move forward, you'll see how this would help us to understand the motion. Okay, so from here, we're going to talk about curvilinear motion. You can generalize it into 3D, but remember, everything we discuss in this course is going to be 2D motion, which means motion in a plane, right? So for the motion in plane, you don't need the Z or the third dimension. It could be like X and Y, R and theta, or N and T, as you see here. So the first coordinate system, which you're familiar with quite well, is Cartesian coordinate system. Remember, we said if we want to understand the motion of a particle, we need three things to know: position, and if you make displacement part of position is this displacement, then velocity, then acceleration. We're going to start with position here. Suppose that this blue curve is the path of motion for this particle P. We have Cartesian coordinate system X, Y, Z fixed at this point. And you know, if you want to find the position vector, you go from origin to the point P. This R is going to be your position vector. And in Cartesian coordinate system, you can express it by X, Y, and Z component. X and Y and Z are the values of this length, and this length respectively. And I, J, K are the unit vectors. Do you guys know what the unit vector is? I think is the name tells us what. Jake, what is a unit vector? Like I, J, K, what are they?
They're in the direction of like the actual vector, but they only have a magnitude of 1.
Exactly, yes. So they are a vector, so they have magnitude and direction. Like here, I and J and K are always in direction of X axis, Y axis, and Z axis. So they're technically constant vectors, and their magnitude is 1. So goes this way, 1 unit, goes this way, 1 unit, and goes this way, 1 unit, right? So this is the position. If you want to find displacement, you can get the difference between two positions, but this is from your, again, math. To find the length of R, the vector R, you can get the square root of X squared, Y squared, Z squared. So that's the length of R. So to get the displacement, you go from point 1 to point 2. Your position vector is going to be R1, and the final is going to be R2. So you're going to get X1, Y1, Z1 for R1, X2, Y2, Z2 for R2. And then if you subtract them, This is what you're going to get. So technically, your delta R is delta X times I, delta Y times J, and delta Z times K, right? Which means you can consider the displacement in X direction, in Y direction, and Z direction. It looks kind of independent, right? Because X doesn't interfere with Y, Z doesn't interfere with X, so each of them has its own stuff. Make sense? Now, what comes after position and displacement? Cristobal, what else we need to know to understand the motion of particle P?
Velocity.
Velocity. By the way, did you guys print this course notes? I think it would be helpful. This is what I can recommend you. I put 2 slides in 1 page in the PDF file. If you print it one-sided, and if you solve problems or take notes, when you put it in a folder, you look at one side, you can write your note on the back of the next page. So you see the slides and you see your notes. This is the possibly the most, because I know some of you guys are used to write your own notes, but because of this graphics and R's and this vectors and shapes, it might be easier just to print them and write your notes on the back of the next page. So when you open the 2 pages, you see the slide and you see your notes. That might be the most efficient way. And the other thing is, when you look at your notes, you remember the slides. Hopefully you remember what we talked in the class. I mean, we have the videos, but that would be maybe more efficient to do it anyway. So then it's going to come velocity. For the velocity, we take the time derivative. You know what? Let me just do this in tablet, so we see what happens next. Because it might be easier to let me share the screen here. So we go to the notes. So to start, we start with position vector R, as I said, is xi plus yj plus zk. Right? Now, we talked about velocity, which is the time derivative of position vector. So I'm going to put the dt of this guy, xi plus yj plus zk. Remember, I, j, and k are constant vectors, so they don't have time derivative. So if you do this, your v is going to be dx dt times I plus dy dt times j plus dz dt times k. So in dynamics, when we have the time derivative, we usually express it with a dot on the top of the letter. So this is going to be x dot I, y dot j plus z dot k. Now, velocity is a vector, right? I can express it in terms of x, y, z component. So if I do that, this is the x component of velocity, this is the y component of velocity, and this is the z component of velocity, correct? Because x dot comes with I, y that comes with j, z that comes with k. So if I want to rewrite that, can I write v as vxi plus vyj plus vzk? Can I do this? So technically, vx is the component of velocity in x direction. Vy is the component of velocity in y direction. And vz is the component of velocity, regardless of whatever the vector is, right? Now, if you compare these two, you see that this, and this are the same, which means x dot is the x component of velocity, y dot is the y component of velocity, and z dot is the z component of velocity. Does that make sense? Interestingly, it looks like when you analyze a motion in Cartesian coordinate system, you divide it into x, y, z from the beginning, and then the velocity components are also independent. You see it in VZ, we don't have y or y dot or x dot or anything. VZ only depends on z, Vy only depends on y, and Vx only depends on x, right? Now, this is how you get your velocity. You can use one of these two equations, either this guy or this guy, which are the same technically, right? Now, the next step is going to be acceleration. To find acceleration, A is dv dt, right? The time derivative of velocity vector. Now, if I remind you what v was dx dt I plus dy dt j plus dz dt k, right? If I take the derivative of this, your A is going to be so that's how you get it. Again, we're going to do the time derivative of these components. Once more, I, j, and k are constant vectors. They don't have derivatives, right, Kelly?
Right.
Yeah, okay. So what remains for derivative is going to be this term. So the time derivative of dx dt is going to be d2x dt2 I d2y dt2 j and d2z dt2 k. Again, these are time derivative. For one derivative, we use one dot. For second derivative, we use two dots. So technically, A is going to be x double dot I plus y double dot j plus z double dot k. Any question? Once more, if we consider that A is a vector in Cartesian coordinate system, the component that comes with I and the components is going to be AX. The component that comes with J is going to be AY. And the component that comes with K is going to be AZ. So technically A is AXI plus AYJ plus AZK. meaning that AX is X double dot, AY is Y double dot, and AZ is Z double dot, right? Again, you see the X component of acceleration only depends on X. The Y component of acceleration only depends on Y. The Z component only depends on Z. So practically, when you analyze the motion in Cartesian coordinate system, it looks like three particles moving on a straight line, right? Each of them has one component, X or Y or Z. And that makes the analysis much easier. Any question? And that's how we get to this thing. Now, if we go back to the slides, this is technically what I meant. dr dt x dot I, y dot j, z dot k, which is vx, vy, and vz components respectively. And for acceleration, x double dot, y double dot, z double dot, which are x and y and z component of acceleration. Now, can you notice something in this plot or in this graph or figure? Haojin, what do you see here for velocity? What is specific that we talked about before?
I think Vx equal 0.
No. In terms of, you see, this is the path of motion. And this is velocity. Remember, we said velocity has a certain character that it's always true. What was it? Anyone remembers?
Tangent to
the path, exactly. You see, it doesn't matter how much Vx, Vy, and Vz is. Their combination has to be in a way that the overall velocity has to be tangent to the path. This could be a 2D curve, it could be 3D curve, regardless, velocity always tangent to the path, right? So sometimes this could give you an extra equation to find something. But for acceleration, there's no such a thing. It's just arbitrary and it depends on AX, AY, AZ. You see, this is neither tangential nor normal, it could be anything. Does that make sense? Any question? Okay, this is a good class. You learn everything in the first try, so I like that. Which means I'm going to give you more difficult exams, right? Because you're very smart. And is that right, Callie? When you don't ask questions and you understand everything, I'm going to raise the bar and give you more difficult exams. That's how it goes. Okay. Maybe that encourages you to ask some questions. We'll see. Okay, so as I said, when you do this, because position of X, velocity of X, and acceleration, they're all X dependent, or Y dependent, for Z dependent. It looks like the X and Y and Z component can be studied independently. They don't interfere with one another. You will see in the other coordinate systems, that's not true. But for Cartesian coordinate system, that is true. Now, an example of Cartesian coordinate system that we use very frequently in different areas could be the motion of a projectile. Now, I'm not sure how good you can see this video, but this is a nice example of projectile motion. If it works. Oops. Could you see anything? So technically, I'm going to do it one more time. The guy hits the ball, the golf ball, moves here. You're going to learn that this is a projectile motion. It's this, plate or board, and then jumps like this. This is another motion of projectile. And when it comes here, it hits it with the club. You see, ball comes all the way and then hits it. And that is interesting. This act has 3 projectile motion. One, when it hits it and goes here, we're going to talk about that. One, when it hits the board and moves on this. And one after he hits the ball and moves all the way. So what is the property or characteristics of a projectile motion, the way we analyze it? Let me ask you this question. If you shoot a bullet with a gun, the path of motion, the way the gun goes, is it a projectile motion? You may not even know how we define it, right? Let me define it first. The projectile motion is you give an initial velocity to an object, to a particle, and let it fly only with the influence of gravity, right? Of course, when you kick something upward, the gravity pushes it downwards, so it kind of goes on a curve, like this golf ball you saw. Now, let me ask you this. When you shoot a bullet with gun, is it a projectile motion?
Yes.
Yes.
But it doesn't go on a curve, right? It goes on a straight line. Does it? Andrew says no. It goes on a curve.
Yeah.
Yeah, it goes in a parabolic arc.
Technically, it does, because the speed is too much. In short distance, you almost see a straight line. That's why those snipers that take a shot in like half a mile or something, they have to calibrate and adjust for those curvature. How about when you kick a ball, like a soccer ball, basketball, throw it, ping pong ball, tennis? Is it a projectile motion?
Yes.
Yes. How about a missile?
No,
Why not?
because it has a thruster on it, so it's getting additional force the entire time.
Exactly. So for something like a missile or things like that, because remember, for projectile, you give an initial velocity and let it go freely. I mean, it's not free because it's under gravity, but nothing else. But when you have a missile or those space, stuff that goes up, they have thrust that move them. So those are not projectile. I just want to make sure you understand what projectile is. Initial velocity and free motion under influence of gravity. Now, if that's the case, it makes it a good example to use Cartesian coordinate system. First of all, if there's no lateral wind or you don't do crazy stuff like the soccer bend or tennis things, which we don't talk about, those aerodynamic effects, right? When you kick something, it goes in a vertical plane. We can specify that vertical plane with X and Y coordinates. So there's no Z, it's like two-dimensional motion, right? X is horizontal, Y is vertical. If I hit this object or give it an initial velocity of V, I can divide that velocity in X and Y component, right? And at any moment, like here, I can divide the velocity divided in X and Y. This is the question. We know that in Y direction, we have gravitational acceleration, which is constant. Now, let me ask you this to see who remembers. Is G, the gravitational acceleration, is constant or it varies?
It varies
Constant.
slightly.
It varies, but if it technically depends on the elevation, right? So if you kick a soccer ball or like the golf and stuff like that in few hundred feet or yards or meters, the change of G is negligible. So on the ground surface, on the earth surface, we can consider it constant. But if it goes like, I don't know, 15,000 meters above the surface of the earth, then you have to consider that variation. So for our purposes, G is constant. Now, the next question, do we have any acceleration in X for the case of projectile?
No.
No, right? You may say if you kick something, it's going to be the air friction or air resistance. Remember, we neglect all of those, right? So the only acceleration is in Y. So technically, if we consider Cartesian coordinate system separates X and Y motion like independent motion, in X direction, we have a motion with constant velocity, right? If you consider the project image of this particle in X direction is like a dot moving left and right. Is it correct? Imagine I kick this ball in a dark, if you look from the top, I don't know if you can visualize it. If you are above this, you see the dot goes left and right on a straight line, correct? Now, if you
Yes.
are right in front of that ball, it's like a illuminating ball, you see the ball goes up and down. You don't see the X motion, right? So that's how you can separate. The X component of motion is a motion with constant velocity. The Y component of motion is a motion with constant acceleration and is rectilinear motion because X is a single parameter moving left and right in this line, and it's up and down on this line. Does that make sense? So you see, for a motion like projectile, it's easier to use. Can we use normal, tangential, or polar coordinate system? Of course. But analyzing with those coordinate system makes it very difficult, as you see later, how the equations turn out, right? But with X and Y, it makes it very easy. Now let's develop the equations. Because gravitational acceleration is Y direction, and there's nothing in X direction, technically, your vertical motion has a constant acceleration. These are the equations we had for linear motion with constant acceleration. Do you remember this? I want you guys to write this down, and then I'm going to compare it to what we had for rectilinear motion. Okay? Are you guys finished writing?
Almost.
Okay, take your time. We can be here all day till midnight. I'm free today. Done?
Yep.
Okay. Now, let's go back to the, you wrote this stuff. Let's compare them with what we had for rectilinear motion with these guys. You see constant acceleration. V is V0 plus A constant times T. In our case, A constant is minus G. So if you substitute minus G here and minus G here and minus G here, you practically end up these equations, right? Now, this is for Y component of motion, constant acceleration. For X component of motion, there's no acceleration. So technically, Vx is going to be constant, whatever it was at the beginning, which is like Vx, V0 in X component. And displacement, if you get acceleration as 0, this is what you're going to get, right? So you divide your motion into two components in X and Y, one with constant velocity, one with constant acceleration. Remember, at any moment of time, for example, you release this, after 2 seconds, it comes here. This is going to be your X, and this is going to be your Y. You calculate your Y from here and your X from here, and you find the position. At the same time, you can find Y component of velocity and X component of velocity and add them together as vectors, and you get the overall velocity, which is supposed to be tangent to the path. You see, even here, they draw a tangent to the path and tangent to the path. So technically, if this is the position vector, X component is this guy, and Y component is this guy. Any question? You had seen some of this before, right? So we are paying tuition for something you already know. That's cool, right? Don't worry, we get to the new stuff very soon. Very overwhelming. I don't want to scare you, but I'm kind of scare you anyway, right? Now let's do an example. This is, we do one example with the general XY component, no projectile. And we do one example with projectile to see how this works. While you're writing this down, I'm going to do it myself on my tablet so we can move forward with this thing. So as you can see here, you have X and Y coordinate system and a curvilinear motion. And the path of motion is given as Y equals 0.5 X squared, right? It says if the components of velocity along X axis is this 5t, so Vx is variable, depends on time, and is 5t. It doesn't say how much is Vy. It says determine the particle distance from the origin O when t is 0. Sorry, when t is 1 second. And it says initially the particle starts from origin. So x0 is 0, y0 is 0 at t equals 0. It doesn't say its velocity is 0, right? Of course, if t is 0, Vx is going to be 0. We don't know about Vy, so we're going to find that, right? And go from there. Did you guys take the notes? Right? Okay. Now let's go to my tablet and solve this problem. How we should start, how we should solve this? This is the problem, right? I just summarize it here. Sorry, my X and Y. You know what? Let me just fix this. I probably should do a better job. So let me just get rid of these things. Okay. Using some technology here. How we're going to solve this? We know that X at t equals 0 is 0, right? And Vx, sorry, Vx as a function of time is 5t. Technically, if this is the case, how much is Vx? 0. At initial time equals 0.
0.
Yeah, of course, 0, right? Now, if that's the case, and you will be surprised how quickly I forget things. I forgot what the problem asks for. It asks for the magnitude of acceleration. Okay. and the distance from origin after 1 second. Okay. So to find acceleration, how I can find acceleration of x or acceleration of particle in x direction? Remember?
The
Go ahead.
take the derivative of the velocity.
Yes, remember I said the way we look at this, if you project position of P here, we can call this Px or x of P. Let's just read x of P. And then if we project in Y, it looks like we have a particle moving on a straight line in X and Y direction, right? Independently. So if that's the case, I can take the derivative of this. So AX is going to be dVx dt, which is d5t dt, and it's going to be 5, right? Meter per square second. What are the units? Let me see. The units, it says feet per second. So this is feet per square second. It's not meter. Okay. How I can find the position of particle in x direction or xp? Ricardo,
From
let me ask Ricardo. How I'm gonna find xp?
So next we have to. Actually, I'm not sure.
Now, William, you were gonna answer?
from the equation you gave us, I think x equals velocity initial plus acceleration times t.
Or we can say xp of t is going to be d, sorry, not d, integration of vx dt, right? From
Yeah.
0 to arbitrary x or arbitrary t. Remember, as I take the derivative of velocity to find acceleration, I take the integral of velocity to find displacement, right? So if that's the case, you're going to get from 0 to t, 5t dt. So you're going to get 5 by 2 t squared from 0 to t. So your xp of t is going to be 2.5 t squared. Because at 0, it's 0, right? Initial displacement is 0. That's what it tells us, right?
Mhm.
So I'm going to summarize this. I know x of p as a function of t is 2.5 t squared. Vx of p as a function of time is 5t, and ax of p as a function of time, of course, is constant. Now, how I'm going to do the same thing for y, because it doesn't give us much about y, except this guy. Oops. Right? Remember, we said that xp and yp are independent in terms of motion on the x, but they are not really independent from overall, right? Their constraint is they have to move on this curved path. So it's not that y could be anything regardless of what xp is, right? They depend on one another because of this path. Make sense? So if y is half of x squared, and this is my x, I can get the y right? YP, which is 0.5 x squared. I'm going to put x from here. 0.5 times 2.5 t square, right? So let me write it here. So YP as a function of time, it's going to be 0.5. 2.5 squared is going to be 6.25. And t squared is going to be t to the 4. And if you do that, you're going to get this times this, you're going to get 3.125 T4. Am I right? So if my X goes like this and my Y goes like this, then the particle P is going to move on this curve, right? Because we relate X and Y with this equation. Do you guys follow? Now, okay, I want to find velocity and acceleration component in Y direction. How am I going to do that? How about Vy of P as a function of time? Should I ask from the female portion of the class?
That would be like the derivative of,
Exactly. It's going to be dyp dt, right? Which if you use this, you're going to get 3.125 times 4 t cubed. And if you do that, this times 4 is going to be 12.5. Right? And the unit is going to be feet per second. Here, the unit is feet. Correct? And if I want to find acceleration in Y direction, it's going to be dvy dt, which is going to be the derivative of this is going to be 12.5 times 3 t squared, which gives you so I got position, velocity, and acceleration in Y direction. Now, how I can find the magnitude of position, acceleration, velocity of particle P? Because first of all, if this is particle P, I know that its velocity has to be tangent to the path, right? How it goes, how long it goes, this vector, I don't know, but it has to be tangent. Acceleration, it could be anything. Any question? So the problem asks us to find the particle's distance from origin. So technically, we need to find this vector, the length of this vector r. Can you see that? Or maybe I made, you know what, let me just redraw that. If this is x and y, and this is particle P, right? Then the length of this r is going to be the distance of P from origin. How do I find that? I'm going to get x squared plus y squared. By the way, it asks at time equal 1. So if time is 1 second, xp is going to be 2.5 and yp is going to be 3.125. You guys substitute here and tell me how much r is.
About 4.
Just give me with a couple of decimal digits.
4.002.
Okay, that's very close to 4. Yeah. Then how about velocity of p? Again, you have x and y component of velocity, right? If you look here, please stop writing and pay attention to the slide, to the screen for a second. If this is the velocity of p, which is tangent to the path, it's going to have vpx and vpy, right? How much is this? Again, if you want to calculate that, you're going to get vp is the square root of vpx square plus vpy square, like any other vector. If you substitute t equal 1, vpx is going to be 5 and vpy is going to be 12.5. So it's going to be 5 square plus 12.5 square. You get the square root, give me the number.
13.463.
And the unit feet per second. Remember, we are engineers, right? Because if you are accountant, if you say a number is usually money, dollar, right? If you are project management, is either time or money. But as an engineer, when you say 52, we deal with so many different physical parameters. If you don't give me the unit, that number doesn't mean anything, right? Please make sure you never forget the unit, feet per second here. How about acceleration? Same thing. APX square plus APY square, and you take the square root. And again, looking at this, APX is 5. APY is 37.5. Did you get the number?
37.832 feet per second squared.
Good. You guys get the same number? Okay. So that's how you analyze Cartesian coordinates and the curvilinear motion of a particle. Remember, I said it looks like you analyze. If you guys are done writing, just pay attention for a second. I said it looks like we have an independent motion in x direction and an independent motion in y direction, but they are not really independent. The relation between those two motions comes from the curve, right? But when you project x and y, then you can analyze them independently. So this was one example. The next example is going to be a motion of projectile. Let me go back. Any question about this, by the way? We're good with this? If I give something like this as a quiz, can you guys do it right now? How many of you cannot do it? And don't feel shy, because it's okay if you can't do it immediately. So everybody can do something similar to this, right? Okay, good. I'm going to adjust my exams even harder and harder as we move forward. You guys think I'm joking? You will see the first time.
Maybe with some homework and practice in the way.
Yeah, sure. I will post the homework sometimes by end of today, because we may not finish chapter 12, but I think you get enough stuff to start doing some homework, right? The next problem is about projectile. You have a skier. This is like, Winter Olympics, ski jump. The guy or the girl, doesn't matter. The person, the particle jumps from here, right? With an initial velocity of VA and initial angle of theta A compared to the horizontal line. The initial angle is 25. The initial velocity we don't know. But as this guy goes up and flies here freely, I don't know if a fly is a good word, but moves freely under the influence of gravitational acceleration, it hits the ground here at B. The geometry of this whole path is given. You have a straight line of 100 meter, slope is 345, and this starts 4 meters below where the guy jumps, right? Yeah. The dimensions of technically the X and Y position of the landing point B is given. The departure angle theta A is given. The problem asks to see how much velocity, technically, how much velocity A should be that if it lives with this condition, lands at B, and also how much time it takes to go there. So I'm going to give you a minute to draw these things, and I'm going to do it myself. How do we solve this problem, by the way? Any suggestion or any thought? Let me go to the tablet. This is what the problem is, right? We have the value of theta A as 25 degree. We need VA and we need time. Any suggestion how to start? The first thing is, remember, we talk about Cartesian coordinate system, right? Where should I put it? Let's just create a Cartesian coordinate system. So, okay, this is my X. And this is my Y. Okay. X, Y. Now, the question is, where should I put this guy? Come on.
I would have A at 0, 0.
Oh, it is 0, 0, but where is 0, 0? Now, here's the thing. You can put it here, for example, right? You can put it here. Or you can put it here. Which one you like?
The current one.
This one? Remember, the position of coordinate system does not change the final answer. We can put it here, right? Or here, but now someone asked here, we're going to honor that. I usually, whatever the students go, I'm going to do something else, but this time I'm going to be nice to you guys and do the same thing because I want to show that, oops. Now it's hard to move this right there. Okay. Just like this, okay? So this is my, oops, Y and X, and this is origin O. Okay. Now, what else?
Calculate the position of B.
I think we can write down the equations, see what we know and what we don't know, right? What was the equation or set of equations in Y direction? I'm going to write the Y direction in with black. So we had Y is Y0 plus V0Y T minus G by 2 T square, right? And for X, I'm going to write it with blue. We had X0 plus V0X times T. Correct?
Mhm.
Okay. Now, remember, the point 0 is technically this point A, right? And final point is B. So we are talking about this point and this point. So in this coordinate system, how much is Y0? I'm going to substitute the values here. How much is Y0?
64.
64, because this slope is 345. So if this is 100, this is 60, and that's 4, so it gives me 64. Let me just create less mess here. So you're going to get, how much is the final Y for B?
80.
Y.
What do you mean?
The Y
that starts
component
at 0?
of position 0, yes, right? So, because I'm going to substitute values, so you get 0 is equal to 64 plus initial velocity, which is at the Y component. If I project this velocity, this is going to be V0Y, and it's going to be V0X, right? And this angle is theta A, which is 25. I'm just going to keep theta A. So this guy is going to be V0, which is VA times sine theta A times T minus G by 2 T squared, right? This is one equation, correct? Now I'm going to go with the blue equation. Let's call this as equation 1. And I'm going to call this as equation 2. So that was 1. This is 2. For 2, how much is the final x for B?
80.
80. How much is the initial x, which is x of A?
0.
0, because A is on y-axis. 0 plus Vx, which is going to be VA cosine theta A times T. Correct?
Mhm.
Equation 2. Now, I have 2 equations here. How many unknowns I have? Do I need to create or find more equations than I'm finding here? How many unknowns I have? Look at here.
2.
VA, I don't know it, right? Sine theta, I know it, so that's not unknown. G is gravitational constant, I know it. The second unknown is T. In this equation, same, VA and T. So these 2 equations technically gives me 2 unknowns of VA and T, and you can obviously solve it for those values and just find the VA and T. Okay? I'm going to give you 2 minutes. Substitute the numbers. And please, everybody, I know this is like middle school math, right? 2 equations, 2 unknowns, very easy. But please make sure you do it so you get familiar with the equations. And let me see, I don't have the printed version of the solutions with me. Let me see if we can find it in the solution manual, find the number and give it to you guys. Or compare that, please. What was the problem? 101. Yeah, I have it here. Okay. If you find the value for VA and T, let me know. I can write it down so we can compare with the others.
Point A.
How much?
Were equations 1 and 2 in reference to point A?
Equation 1 and 2 are related to technically point A and B. Remember, y here, let me highlight it. This y is actually yb, the final position, and this x is xb. The y0 and x0, y0 and x0 belong to A. Technically, initial and final point. This is your initial point, this is your final point, and you move like this, right? So anyone got any number for this? So I'm not going to spend too much time. You can calculate it later. Let me just give you the numbers. So if that's the case, and you calculate this, you are going to get as, technically what you can do is this. You can calculate T from here. T is AT over VA cosine 25, right? And then substitute here and calculate your VA. And then go back and calculate that one. So if you do that, VA is going to be 19.42 meter per second. And time is 4.545 seconds. Did you guys get something similar or anything at all? You can check it later, that's okay. So we can move on to the next part, but I give you the numbers, right? Any question about the content? Remember how we started? We started with position for the y component of position and x component of position. Remember, initial and final. Final is B, initial is A. We are talking about 2 points, initial point and final point of the projectile, right? So there's always that case. And then after writing the equations, 2 equation to online, you can solve it. Any question about this one? Now, you remember I mentioned the other day that dynamics has a wide variety of problem solving technique. Like last problem was completely, I mean, not completely, but it was somehow different. We had to calculate X component and switch to Y components. This one is a projectile. You get X and Y and you relate them to find the unknowns. If you go to the textbook, there are like maybe 20 different problems for projectile. Each of them is solved differently. So you may need to practice some of them. Okay, let's go back to the screen. Now, because we're going to stop a new concept, I'll give you like 2-3 minutes of break. Okay, kind of you refresh your memory and we go back. I'm going to pause the recording. I'm going to share the screen. So the next coordinate system we're going to talk about is normal and tangential. It's not something you had seen previously in your math courses, but you will see how useful it is to analyze some particles, motion and characteristics. The way this system works is this. You will still have a curvilinear motion, so particle P moves on a path. The position of P is determined from an origin and with the length of the curve. You may realize that this is a good way to talk about, for example, driving in highways and roads, because you cannot give your, XYZ coordinate system or polar coordinate system when you leave a town, as I think we talk about that, when you have, let's say, I don't know, flat tire or something, say, hey, I'm out of Edwardsville towards Chicago, like 55 miles out, or someplace like that. So when you say out of Edwardsville is going to be your O reference point. This is going to be the highway, and 55 miles is here. So people can just easily find you, right? So that's a good way to address the position. Now, the unit vectors extends instead of I, J, K, you have a unit vector tangent to the path at any time and normal to the path at any time. So obviously, unlike I and J and K, these are not constant unit vectors because, for example, when P is here, UT is in this direction, but when P is here, UT is in that direction. So the tangent to the path, the direction of tangent changes. Remember, still unit vector, the length is 1, but a vector is made of magnitude and direction. Each of them that change, the whole vector changes, right? So if the direction of UN and UT change, they're not constant vectors anymore. Is the definitions clear? How we define the position, how we define the unit vectors. Remember, normal to the path is always toward the center of curvature, right? Do you guys remember center of curvature and curvature, the value of curvature for a curve from your calc stuff? No? Let me explain that on the tablet so it's kind of refreshing your memory before we move forward, because we're going to talk about that later. Share the screen.
Position over velocity, the magnitude.
No, the curvature is about the geometry, right? Forget about velocity. It's just like pure math. Imagine, let's say, again, like you have a function, right? Let's say this is your X and Y, right? And then you have a function like this, Y as a function of X. Something, right? The curvature of a curve at each point is defined like this. Assume that, let's say this is like point, for example, P. How we define the curvature, and I'm sorry, I cannot draw this properly because it doesn't give me other tools. But if I draw a circle that is tangent to this curve like that, right? The radius of that circle is the radius of curvature, and this point O is the center of the curvature. The radius of curvature, we usually use the Greek letter rho. So practically, if you have a curve like this, to find the radius of curvature, it's like you cut a little bit. This is a part of a circle, right? That tiny bit is part of the circle, and that's how you do. Do you remember that now? So for example, if you have a very sharp curvature, the radius of curvature is smaller. If you have a smoother or a wider curvature, the radius of curvature is going to be bigger, right? That's how it goes. In this coordinate system, we deal with this. So when we talk about, okay, this is a path of motion and this is particle P, right? This is going to be UT, and this is going to be UN. And then the radius of curvature, if I draw that circle thing, right? This is going to be rho, and this is going to be center of curvature. This is a little ugly, but okay. So UT is technically tangent to this circle, and UN is perpendicular to the path that goes through the center of the circle. Do you remember something? Okay. Now with this kind of reminder, let's go back to the slides. So that's how we define UT and UN. Now, in this case, we do not use the position vector, right? We use this length S to give the position. And as I said, N and T will be variable. So somehow, if this is the particle moves on a circle, goes through different curvatures. I'm sure you all have been driving your cars in highway. You experience that every time you drive somewhere, right? Now, the normal axis, we call it unit vector UN, UT, I explained those, right? UT is tangent to the path. UN goes toward the center of the curvature. I explained that, right? Now, for the position, as I said, you use this length S. The radius of curvature at any time you have a small ds, it looks like this is a part of a circle. You see, this is sharper, you get a smaller row. These are more kind of flat, you get larger row. And even the center of curvature changes as you move. That's how the geometry works. Any question about the geometry? I think it's kind of clear, and hopefully it reminds you stuff that we talked about, or you learned it in, I think it's Calc 1 or something. Did you guys study radius of curvature of functions? No, William? I'm sure you did.
No.
You don't remember
Maybe.
maybe, but it must have been covered in Calc 1, the calculus, when they talk about derivatives and stuff like that. So if this curve is given as a function of x, y as a function of x, the magnitude of rho at each point is going to obtain from here. dy dx squared plus 1 to the power 3 square root divided by the second derivative of y with respect to x. And remember, radius is always positive. You can't have negative radius, right? So this is positive. That's why we get the absolute value of this to get the positive value for rho. So this is how the geometry works. Any question? Have you guys seen this equation? Yeah, Cristobal says, I'm sure this is not something you deal with every day. It's okay if you have forgotten. Now you have it. And of course, we have online tests. You can look at your notes and stuff, or if usually in the in-person class, I allow students to have a formula sheet so you can write it down. It's not complicated, but if you don't memorize it, that's okay, right? When I was your age, I could memorize it. Now I have no chance to memorize anything, so I just use notes and stuff like that. So this is the geometry. If you talk about displacement, you go from point 1 to point 2, right? You get from S1 to S2, so your displacement is delta S. Or if it's a very small, ds. And remember, S is the length of the curve, is not the direct line between 2 points, right? The same way you drive 50 miles, you don't consider initial and final. A straight line is not 50 miles. The path of motion, the length of the curve is 50 miles or whatever it is. The next one, velocity. If displacement in ds, the velocity is going to be ds dt, right? Or s dot. Still, velocity is a vector. So its magnitude is ds dt or s dot, or you can call it simply v, because we have only one component of v tangent to the path. And technically, this is the number, again, you read in your speedometer of your car, right? Now, I think all cars have this digital speedometer. It goes like 42, 47, 49, 52. You push the brake up, comes back to 37, 32. The number you read is the instant velocity, which is this ds dt. How about the direction? What is the direction of velocity?
Tangent to the curve.
Tangent to the curve, right? So now you see why this coordinate system is nice and makes life easy. Because velocity is tangent to the path, and go back here to the previous slide, the tangent unit vector is also tangent to the path. So you can use that guy, right? And express it like this. The magnitude times unit vector. So V is technically the magnitude that we get from here times unit vector. So you just need one vector to explain your velocity, and it's the tangent unit vector. Does that make sense? Isn't it nicer? You don't have X and Y, because sometimes X and Y doesn't give you physical meaning, right? How about acceleration? What is acceleration? How we get acceleration? Let me go to the slides again so I can derive it there step by step, and you see how it goes. So to find the acceleration, the velocity as a vector was v times ut or s dot times ut, right? So technically, we have two terms here, v or s dot and ut, right? Is ut constant? Because when we had ijk were constant, the derivatives was very easy. Is ut constant?
No.
No, we talked about that. The length is unit, but as the curve changes, I'm going to show you here. Let's say this is a curvature, right? If you are here, this is ut. If you go here, this is ut. You go there, this is ut, right? So while the magnitude is the same, the direction changes, so it's not a constant vector. For ijk is always like this, right? Doesn't matter where you go, it's just same thing. But here, no. Is it clear now? Okay, now to find acceleration, what was the equation for acceleration? Was dv dt, right? Is it correct?
Mhm.
Okay, now I'm going to substitute v here. I'm going to get d dt of v ut. Now again, for ijk, that guy was constant. We just take it out of derivative. But here, this is not constant. So you have to have dv dt ut plus v times dut dt, right? Product rule. dv dt, remember v was s dot, so dv dt, you can call it v dot or s double dot, right? This is technically the number you see. I mean, you don't see it directly, but if when your velocity changes, when you drive your car, 50 miles, 70 miles, 62 miles coming up and down, this s dot, s double dot, or v dot is the change of that number. Okay. Now the question is how I'm going to get the derivative of du dt. To do that, there's a derivation in the book. I'm not going to drive it all the way through, but I'm going to show you what happens. Let's just make that curvature much larger. Okay, this is your curvature. This is your P, and this is your P prime. And technically, this is the ds. This is very small, but I've kind of expanded to show how it goes, right? The tangential unit vector here is ut, and here, let's call it u prime t. And this is p prime. So du dt, I have to find du first, right? Which means the change of the vectors. If I redraw them side by side, this is like ut. This goes slightly up and becomes like that. Right? The difference between them, which is technically du, let me just put it here. dut is going to be u prime t minus ut, right? If this is u prime t and this is ut, the difference between them is going to be this guy. Correct? Is this right?
Yes.
The difference between the two unit vectors is a tiny red vector. Now, remember, this is a differential. That means this is a very infinitesimal, which means this angle theta is going to be very small. As we take the limit and this length becomes smaller and smaller, this becomes perpendicular to ut, right? The direction. Does that make sense? In the limit form, when this d theta becomes smaller and smaller, this becomes 90 degrees, right? Now, if this becomes 90 degrees, which direction this shows? If this is ut, what is this direction? Look at your notes. We called it un, right? Normal direction. So technically, this guy becomes a vector in un direction. And its magnitude is going to be v over rho. There's a derivation. I'm not going to go through the derivation. You can look at the book. If you need help, we can talk about it in the office hour, right? But technically, du dt becomes v over rho un. Okay? Now, if I substitute here, the entire term is going to be v times v over rho un, right? And if I rewrite it, let me just clean this part. if I write the overall equation A as a vector, is going to be v dot ut plus v squared over rho un. And this, you know, you can also write s double dot. So this is your acceleration, right? You remember on Monday, I asked you tangent, velocity is always tangent to the path, and try to confuse you. Is acceleration normal or tangent to the path? Some of you said normal, some of you said tangent to the path, and I said it's neither of them, right? If you look at here, you see your acceleration has a component tangent to the path, and it has a component normal to the path. And any of them could be zero technically, right? Now, again, you see why this coordinate system is nice to deal with. It's easier to express it, right? So v dot is technically vt, and v squared over rho is vn, normal and tangential component of the acceleration. Right? So as I said, v dot is the change of the magnitude of the velocity. And this is due to the change of direction of velocity. Okay. So how one of them could be zero? If your velocity doesn't change the direction, right? You go on a straight line, this guy will be zero. Right? If you
Shouldn't
move,
the v dot equal a of t or a sub t, not v sub t?
yes, thank you. I don't know why I wrote a v. Yes. That's a good observation. I get excited, I make mistakes. Tangential component of acceleration, normal component of acceleration. Thank you. Right? So what was I saying? If you move on a straight line, there's no change of direction. This is going to be zero. If you move on a circle with constant or any curve with constant speed, for example, you set your cruise control on, I don't know, 75 miles an hour or 70 miles an hour and let the car go. The speed doesn't change, right? Then this guy will be zero. Does that make sense? So that is how you express velocity and acceleration based on tangential and normal component. It has a physical meaning, so it makes it nice to analyze the motion that way. For velocity, you have only one component of vector, which is in t direction, which is, we know, in the tangential direction. And for acceleration, you have two components. Each of them has a different physical meaning. V dot means change of the magnitude of velocity. V squared over rho means or comes from the change of the direction of the velocity, right? Any question? Now, if you analyze a motion in Cartesian coordinate system, you get Vx, Vy, Ax, Ay. They don't have specific physical meaning, right? AX doesn't mean much. It's just you get the acceleration, X component. But here, V dot has a physical meaning. You can actually look at your speedometer, and as it changes, that's your V dot, right? You can look at the path of driving. If it's curved, I don't know, if sometimes you go to mountains or somewhere, you just, go left and right and left and right. And this is the component of acceleration you feel there. Any question? Are we good?
Can you
Okay.
scroll down a little bit to show what dut over dt is?
Yes.
Thank you.
So if you go to the slides, it's the same derivation here, but I thought sometimes it might be easier to write it down step by step. So for the acceleration, you get v vector dot, which is dv dt. You separate them. This is product rule. You get this component, which is v dot, this component, which is this guy, and then your overall acceleration has a tangent and normal component, and that's how it looks like. Any question? And you can look at this. This is kind of showing how it works. When you go here, tangent is always tangent. By the way, if you increase your velocity, AT is positive. If you decrease your velocity, AT will be negative, which means going backward, right? For example, when you push the gas, AT looks like this. When you push the brake, AT goes backward. But AN is always toward the center of the curvature. Now, this part of the curve, AN is down. You get to this part, AN is up. You go to the straight line, there's no curvature, rho is infinity, that component will be 0, and your acceleration is only tangential. Looks good? Okay, I'm going to stop it here. We are like 11:44. We can solve this problem. We're going to solve these problems next time. And before you go, let me take a screenshot for the attendance. Any question or comment about today's lecture? Did you guys enjoy it? Yes? No? Did you learn anything new? Ricardo say, hey, kind of. It was little suffering, little enjoying, right? Okay. Did you learn anything? Okay,
Yeah.
good. Okay, good. So I will post the homeworks later, maybe today evening sometime, right? So you can start working on them. Hopefully by Wednesday, we can finish this chapter. And next week, we start new chapter. We may have a quiz, and we talk about that later. The quizzes are going to be online. They're going to be activated right at the time and disappear right at the time. You have enough time to solve the problem, scan it, and upload it in a link I provide. I'm going to talk about that later, okay? But for now, if you need help with any of this concept, I'm going to, again, when this recording is, saved on my computer, I'm going to upload it to the Blackboard folder. If you need to watch any part of it, or if you lost connection temporarily anytime, you can go back and have a look at it. But that's how it goes. Okay. Are we good? Okay. Thank you, everybody. And I see you guys on Friday. Today is Wednesday. Okay. On Friday. Goodbye.